Welcome to another problem of civil engineering. This problem has been taken from Engineering Service Examination 2020. This is a very prestigious and most competitive examination in India. So let's see what's the problem. The problem is a beam of length L is fixed at its both end, okay, and so it's a fixed beam and it carries two concentrated load, okay, and the magnitude is W and both are equal, and this act at a distance of L/3 from both ends, okay, and you have to find the fixed end moment at A or B, whatever, okay. So this type of questions comes in this type of examination, which are MCQ in nature, and you have to answer this question within hardly 40 to 50 seconds, okay. So now you may think how it is possible to calculate the fixed end moment for a given load of a fixed beam, okay. If this is the fixed beam, this is the loading, okay, both are W, and this is L/3, this is L/3, this is L/3. You have to calculate what is the fixed end moment at this end. Well, this is a tricky question. If you know the basic things or a particular principle, obviously within this 30 or 40 seconds you can find out what is the correct answer. Well, the purpose of this video is not to use the trick and to tell you what is the correct answer. My purpose of the video is to discuss the basic concept behind this problem, okay. So let's start. First, consider any particular beam, okay. Let's say this is a beam, okay. I am not saying anything about the support condition. Now consider any two cross section. Let's say this is one cross section and this is another cross section, okay. And now when you apply any load on this beam, what happened? This beam simply bend like this. Let's say this is the shape of the beam after bending, okay. And you know how to draw the bending moment diagram. Let's draw the bending moment diagram. Let's say this is the bending moment diagram. You don't know what is the type of loading, it may be any type of loading. So let's consider this is the bending moment diagram, okay, and this is the deflected shape. Now you have considered two sections. Well, one section is here, another section was here, clear. Now can you see that in this case the rotation of the section or rotation of the tangent here is 0. That means the tangent at this point and at this point is simply collinear. But here, what is the tangent? Let's say at this point the tangent is like this, but at this point, let's say this is the tangent, okay. So you can say that your tangent has rotated like this, okay, in this direction it has rotated, clear. Let's say this is a very small length and it is, let's say, ds, and d is so small that it tends to 0. And now due to this rotation, let's say this angle or this rotation, okay, this is also very small, and let denote this by your d theta, okay. And here corresponding to this section in this bending moment diagram, it will come here, okay, and corresponding to this section the point will come here, okay. And this curve or this ds length in straight line can be expressed by your dx, and you can say ds and dx are more or less same because both of them are almost 0. Clear? Now draw a perpendicular here at this section. Well, it will look like this. Let's say this is the perpendicular, okay, and again draw a perpendicular here at this tangent. It will look like this, okay. This is the tangent, or sorry, this is the perpendicular at this tangent point. Now can you tell me what is this angle? Well, let's consider any quadrilateral. Let's say this is a quadrilateral, okay, and this is the quadrilateral. This is similar to this one. Well, here the ds is shown by dotted line, and you know this is 90 degree because this is the perpendicular, so this is 90 degree. This is also perpendicular to the tangent here, this angle, so this is also 90 degree. And here, what is the rotation here? This rotation, let's say this is theta, okay. And if you draw it more clearly, you can visualize this. This is the curve. Here was your first tangent, here was your second tangent, okay. If you extend it up to this point, this is your theta, and this is this one, okay. So what is this angle? You know, the summation of all the angle in a quadrilateral is simply 360 degree, okay. What is this angle? Simply 180 degree minus theta. So what is this angle? This is coming as 360 minus your 90 minus 90 minus 180 minus theta. So this angle is coming as theta, okay. So here we can see that this is also d theta, no doubt about it. And in the class of bending moment and shear force diagram, or the interrelation between the bending moment and shear force, you have learned that the bending moment, the moment of inertia of the section, can be related with this formula: may I follow you, Elizabeth Rani. So F is the stress, Y is the distance of the fiber. I have repeated many times in my others videos also. So this is the best way to remember this formula: may I follow you, Elizabeth Rani. R is the radius of this curvature, you know. So if we pick up these two figure, we can rewrite this equation as 1 by r is equal to m by ei, okay. And if this is r and this is rotated by degree theta, what is the distance of arc it is traveled? Well, you know that this arc is r theta, okay. So here we can also write that what was the length here? This was ds, so ds is r times d theta, okay. Or you can write your ds, it is almost equal to dx, so this is dx by r time d theta, and 1 by r is known to you, that is d theta is coming as 1 by r is how much? No, this is m by ei. M is the moment at particular section, m ei times your dx, okay. So here you can see that m by ei, or bending moment diagram, is m. If we divide this bending moment diagram with ei, or flexural rigidity, then we can integrate this curve from this point to this point. Okay, so if we integrate these, m by ei, this is the value, times dx, this is the length dx. So if we integrate this, we will get the change in angle from this point to this point, or from this section to this section. Okay, so theta, or the change in slope between two sections, is given by the integration of the bending moment by the EI diagram. It is not bending moment diagram, rather it is bending moment by EI diagram. And this is the first principle of moment area theorem. Okay, this is the first principle. In another video we'll talk about the second principle, but this problem will be solved by using this first principle. So first principle is clear to you. If we take the integration between 2 points of the m by ei diagram, we will get the change in slope between these two sections. Okay, so come back to our problem. This was fixed end beam. Okay, and for clarity, draw it again. Let's say this is the fixed end beam, and you are applying your load, one here, another is here. This is L by 3, this is L by 3, this is L by 3. And if we take the constant, let's say this is moment MA and this is moment MB, we can remove this fixed support and we can replace this by simply support. Clear? And from this simply support beam and from this loading, you can draw the bending moment diagram because it is known to you. Well, it will look like this. This is the bending moment diagram. And what is the value? Well, if this is W, this is W. From symmetry, the reaction are also W and W. Okay, so what is the moment here? Simply the moment at this point or below this load is coming as W times distance is L by 3. So W L by 3, and this load will create a sagging deflection, so this moment is positive. Okay, again this fixed end beam is under the action of your moment, fixed end moment. We have assumed that we know the moment, that's why we have removed the fixed support and we have replaced this fixed support by pinned support. But for that we have to apply an external moment. So due to this external moment MB or MA, from symmetry it is clear that they both are equal. Let's say they are M. Okay, and they will create a moment like this. Let's say again this one, we are assuming they are acting like this, so the bending moment diagram is positive. Well, draw the bending moment diagram again. It will look like this. Both are M at both end, and this is positive. What is the change in slope from this point to this point? Well, for a fixed support, the slope here is 0 and here is also 0. So theta A minus theta B is 0. There is no change in slope. Clear? Now again integrate this bending moment diagram. Okay, so what is the area? Simply integration means the area of this diagram. So first take this easy one. This is simply M times L. Okay, M times L, and this is positive as per our assumption. And what about this area? Well, this is L by 3, this is L by 3, this is L by 3. okay, and the area of this triangle is half times base times WL by 3, and there are two triangles like this, so simply 2 times, okay, so it is coming as WL by 3 times L by 3, so plus WL by 3 times L by 3. Okay, what about this portion? Well, this is simply rectangle with L by 3 length and the height is WL by 3, so it is WL by 3 times L by 3 is equal to 0. This is the principle, and here you can calculate M. This is unknown, so M is coming as your ML is equal to minus 2 times WL by 3 times L by 3. Okay, if you cancel L both side, so M is coming as minus 2 WL by 9. Okay, so our assumption was wrong. As per the sign indicate, the moment will act in opposite direction, okay, and the value of this moment, fixed end moment, is 2 WL by 9. Well, as I have said earlier at the very first or very beginning of this video, that if you know this principle, this particular principle, to calculate this area, I think you will take hardly 40 to 50 seconds, not more than that. Now let's check whether it is correct or not, or whether there is any option or not. Minus 2 by 9 WL. So B is the correct answer here. Minus 2 WL by 9. Okay, that's all.